Hello students, today I will discuss about the different mechanism of enzyme inhibition and enzyme kinetics. Enzymes are required for most of the biological processes which are required for life. Enzymes catalyze a reaction by reducing activation energy needed for the reaction to occur. The general kinetics and reactions of enzyme. I will discuss about the mechanism of action, transition state stabilization as well as enzyme dynamics. Mechanism of action. First, I will discuss about the single substrate reaction. When a particular single substrate interacts with the enzyme, it lowers the activation energy by stabilization of enzyme substrate complex or transition state. Now, to do so, sometimes distortion of the substrate may happen, sometimes may not. And the flexibility of the active site of the enzyme is sometimes necessary. Enzymes provide an alternative pathway of the reaction. So, temporary with the substrate, it makes ES complex or enzyme substrate complex. Now, it also reduces the reaction entropy by bringing substrate together in the correct orientation to react. So, enzyme overlapping. So, we know that orbital overlapping happens. So, to do so, they comes closer to each other. So, proper overlapping, correct orientation happens. Transition state stabilization. It happens via reduction of delta G or free energy of the reaction. Charge distribution happens via covalent bond formation or electrostatic interaction. Dynamics. Either entire protein domain is involved or active site amino acids are involved in case of enzyme to interact with the substrate. Network of protein helps in protein dynamics. Protein motion is very important for fast vibration, larger and smaller conformational movements, binding and releasing of substrate as well as products. For allostericity, that is binding of ligand at one site can affect the enzyme activity of the active site. The dynamics of the enzyme is very important also there. Enzyme kinetics. Let's start with the single substrate reaction where enzyme reacts with substrate and forms ES complex. The rate constant for the forward reaction is K plus 1 and for the backward reaction it is K minus 1. Now from ES complex ultimately once again the free enzyme is getting released and product is released. The forward of this reaction the rate constant is taken as K plus 2 and the reversible reaction rate constant is the backward reaction rate is K minus 2 which is sometimes here is taken negligible. Now, enzyme velocity versus the substrate concentration. So, enzyme velocity is a function of substrate concentration. It was found that when the substrate concentration is lower, then the initial velocity of the enzymatic reaction that is V0 is proportional with the substrate concentration and it obeys the first order kinetics, the linear increase of the reaction rate with the increase of substrate concentration. But after some times when enough substrate is present, then it follows the mixed order kinetics that is in between first and zero order. When all the active sites of the enzyme present in the medium are getting saturated with the enough substrate concentration, then it is reached to the maximum velocity or Vmax. Fine. So, the V0 versus this concentration of S is quite giving a rectangular hyperbolic curve. Fine. Time course of enzyme substrate formation. Substrate concentration decreases with time, product concentration increases with time and ultimately enzyme substrate formation reaches to equilibrium. Now, Woods and Henry they had proposed that yes, enzyme and substrate they are making a certain kind of transition state or ES complex. Now, this proposal was actually summarized, and some other hypotheses were given by Briggs and Holden. Yes, they have told enzyme substrate complex is produced, fine, but they maintain a steady state kinetics. Okay. Now, what is steady state kinetics? That means when enzyme and substrate, they are reacting to form enzyme substrate complex, first it attains a pre-steady state. Then after that, when ES complex is formed, then rate of breakdown of ES complex is equal to rate of formation of ES complex. That is nothing but this steady state kinetics. Brown and Henry proposed reversible enzyme substrate complex formation and saturation kinetics, saturation effect. In 1913, Michaelis and Menton developed enzyme action and kinetics by proposing equilibrium of enzyme substrate formation. In 1925, this theory was extended by Briggs and Holden by quantitative analysis of steady state concept, that is rate of formation of ES is equal to rate of breakdown of ES. Based upon this steady state kinetics, after that Michaelis and Menton, they had actually given their equation by correlating the initial velocity with the maximum velocity, Michaelis constant as well as substrate concentration, that is V0 is equal to Vmax into concentration of S divided by Km plus concentration of S. Km is Michaelis constant. Now, there are few assumptions of Michaelis-Menten equation. That is, the production of the product is linear with time during the time interval used. The concentration of substrate vastly exceeds the concentration of the enzyme. We have to keep in mind that very, very important point. A single enzyme forms the product. There is negligible spontaneous creation of product without the enzyme. No cooperativity is getting operated here. Neither substrate nor product acts as an allosteric modulator to alter the enzyme velocity. Now, what is the significance of Km? Now, from that V0 versus S rectangular hyperbolic curve that we have seen, the Vmax is attained when the enzyme active sites are totally saturated with the excess amount of the substrate. Now, the substrate concentration at which the rate of the reaction is half of maximum velocity is called Michaelis constant. It is nothing but Km is equal to K minus 1 plus K plus 2 divided by K plus 1. Now, sometimes if K plus 2 is very, very less than that of K minus 1, then Km is equal to Ks, that is the binding constant or the dissociation constant of ES complex. So, it is called substrate constant. It designates the substrate affinity of a particular enzyme. If Km become higher, that means substrate affinity is lower and vice versa. So, Km is molar concentration of substrate at which velocity of the enzymatic reaction is half of maximum velocity. Km is independent of enzyme concentration. Usually, Km is taken as the substrate concentration moles per liter. It is a measure of affinity of the substrate and inversely related. Km vary with substrate to substrate. Isozymes differ in their Km. Km increased in case of competitive inhibitor. Km altered with pH as well as temperature. Km changed with allosteric modulator. Now, the biological significance of Km. So, what we need for better substrate affinity, lower Km. Okay. For leukemia therapy, we know that lowest Km for the asparaginase enzyme is actually found. So, it was found that fungal asparaginase, they have lowest Km, so they can be treated for the leukemia. Now, the isozymic variation of alcohol dehydrogenase causes trachycardia during alcohol ingestion. Once again, very important biological significance of Km value. Now, these Michaelis-Menten equation can be transformed to the linear version. First, Lineweaver-Bach equation, okay? That is 1 by V is equal to Km by Vmax into 1 by concentration of S plus 1 by Vmax. Now, we will know about their plot. Now, when we will know about the plot, we will see sometimes slope become very low due to the scattered points. So, for that particular purpose, we have to shift for other linear equation. Say for example, Eadie-Hofstee equation, where V0 is equal to minus Km into V or V0 divided by concentration of S plus Vmax. It gives the negative intercept. So we can easily calculate Km and Vmax from there experimentally. Hence-Wolff equation, that is concentration of S divided by V is equal to 1 by Vmax into concentration of S plus Km by Vmax. Now let's see the plots. Okay. First, in case of Lineweaver-Burke plot, on one axis 1 by V is taken and on another axis 1 by S is taken, right? So it is sometimes called as double reciprocal plot. We can find that Km by Vm is the slope and 1 by Vmax is intercept on the y-axis and minus 1 by Km is the intercept on x-axis, from where experimentally Km as well as Vmax can be estimated. Eadie-Hofstee plot, it is the plot where V0 by concentration of S are taken, and we can find such kind of plot where over the y-axis Vmax intercept is found and over the x-axis Vmax by Km intercept is found. Here slope is minus Km. In case of Hens-Wolff plot, on y-axis concentration of S by V is taken, on x-axis concentration of S is taken. Here the slope is 1 by Vmax and the intercept on S by V axis is Km by Vmax and intercept on the concentration of S axis is minus Km. Once again from the experiments directly Km and Vmax can be calculated. Other parameters. The second reaction step, that is K2, sometimes is called as catalytic rate. Fine. And from that we can know Kcat, that is the turnover number. The ratio of Kcat by Km defines a measure of catalytic efficiency of an enzyme substrate pair. Now general rules for enzyme reaction, right? So what we have already told, enzyme along with single substrate produces enzyme substrate complex. So shape and the configuration of the both enzyme and substrate may vary, fine. So it gives the specificity of the complementary reaction. And ultimately there are some of the changes in the active site amino acid substrate itself. So ultimately there is the destabilization of the chemical bond within the substrate, which causes the lowering of activation energy. So ultimately this is the consequence of the enzymatic reaction by which the activation energy is getting lowered and ultimately the product is getting formed. Now, by substrate reaction, say for example A and B both are the substrates which are reacting with one enzyme giving rise to P and Q product, fine. Now there are different types of bisubstrate reaction, either sequential or single displacement or ping pong or double displacement reaction. The single displacement reaction is where we can find a certain kind of ternary complex, okay, but it may be either ordered or the random way. In case of ordered way, first the leading substrate binds, then the following substrate. What happens in case of lactate dehydrogenase? Always NAD plus binds first, okay, then only the pyruvate is allowed, ultimately from where NAD plus, NADH and lactate are produced. Now there is the ordering of the binding of substrate, the sequential pattern, okay, for the formation of ternary complex. But in the random process, there is no such order. In case of creatine kinase, either ATP or creatine may bind with the enzyme to give rise to ATP, ADP as well as phosphocreatine. What happens in case of ping pong bye-bye reaction or double displacement reaction? Always two substrate, they do not bind altogether to the enzyme, right? Take example of transamination reaction governed by transaminase, where first amino acid binds with the enzyme. Then there is the change of the pyridoxal phosphate to the pyridoxamine phosphate by acceptance of amino group from the amino acid, fine. Then the first product is getting released from first amino acid to keto acid, okay. Then next substrate comes, that is another keto acid, which takes up that amino group and is getting converted to another amino acid. So the second product is getting released. and the pyridoxamine phosphate, which were actually formed from the pyridoxal phosphate, once again go back to its original state. So ultimately enzyme regains its own structure because pyridoxal phosphate is the coenzyme part of the enzyme. Enzyme inhibition, its kinetics and reactions. The loss of enzymatic activity may be either reversible, where the activity may be restored just by the removal of the inhibitor by dialysis or many other physical processes, or may be irreversible. That means permanent loss of enzyme activity within the stipulated time scale of the interest. So it cannot be regained back within the time, cannot be recovered back. Now enzyme inhibitors, maybe the non-specific one, what we call that denaturants. With acid bases, with alcohol, temperature fluctuation, the protein stability can be destroyed. That means the enzyme activity is permanently lost. But sometimes may be specific, either irreversible or reversible. The reversible one may be the competitive inhibition, uncompetitive inhibition or non-competitive inhibition. Let's discuss about that. The irreversible enzyme inhibition, that is permanent loss of enzyme activity by making a covalent bond of the active site amino acid. What happens? Say for example, if the enzyme contains serine having hydroxyl group, that can make a permanent covalent bond with diisopropyl phosphofluoridate. If it makes it, so permanently the activity will be lost. It can be used commercially as well, mustard gas, as well as many pesticides, just to block the acetylcholinesterase activity, which is acting as a neurotransmitter. Reversible enzyme inhibition. Okay, the first one is the competitive inhibition. What we can find here, the inhibitor binds with the free enzyme. Okay, so it makes EI complex. The example is for succinate dehydrogenase, which is taking part in case of the conversion of succinate to fumarate. Okay, so here malonate acts as the competitive inhibitor of the substrate because it is structurally analog. Now, here we can find, if you follow the Lineweaver-Bach plot, we can find there is increase of the Km value for substrate. Why? Because it is decreasing the affinity, because enzyme gains affinity to bind to the inhibitor as well. Okay, but as ES complex is formed, so no change in the Vmax value. So Km is getting increased here. The next one, reversible inhibition, uncompetitive. The inhibitor binds only with the enzyme substrate complex to give rise to ESI complex. So in first case, what we had found, EI complex is produced. Here ESI complex is produced. Now, so there is a zeal, there is a way to form the ES complex to which the inhibitor binds. So obviously it facilitates the forward reaction. So Km is decreased for that particular substrate here. Okay, and as the ES formation, that is actually late for the final step of the product formation reaction, ES formation is getting disturbed. So here we can find Vmax is also lowered. Okay, so 1 by Vmax become greater. So in this way what we can find, Km is lower, that means ES formation is favored, fine, and Vmax become lower. Okay, so 1 by Vmax become higher here. The reversible inhibition, non-competitive. So before going into the detail of non-competitive reaction, what we have found in case of uncompetitive reactions, so that can be used for many purposes. Say for example, in a cancer cell like a human alkaline phosphatase, they are getting inhibited uncompetitively by leucine as well as phenylalanine. Okay. Now reversible inhibition, non-competitive. Here the inhibitor binds both with the free enzyme as well as ES complex. So here it forms EI as well as ESI. So what happens here? ES complex formation is getting disturbed. So Vmax become lower. So that means 1 by Vmax become higher. And once again there is a zeal for the formation of the ES formation. So obviously Km can be lowered. But once again as the inhibitor binds with the free enzyme, Km is increased. So if two constants, they actually nullify each other, that means no change in the Km value. Okay. The example, some cases the enzymes need some divalent metal ions. Just EDTA, which can chelate all those metal ion, divalent metal ion, can act as non-competitive inhibitor. So let's have a look to the overall reaction kinetic parameters. Okay. So what happens in case of the first competitive one? The equation is 1 by V0 is equal to alpha Km divided by Vmax into concentration of S plus 1 by Vmax. So there is increase in Km value. For uncompetitive one, 1 by V0 is equal to Km divided by Vmax into concentration of S plus alpha prime divided by Vmax. We can find decrease Km and Vmax. The third one, for non-competitive one, what we found, 1 by V0 is equal to alpha Km divided by Vmax into concentration of S plus alpha prime by Vmax. So Km may be changed or may not be changed, but actually Vmax is decreased. So what is alpha? Alpha is equal to 1 plus concentration of inhibitor concentration divided by Ki. Ki is rate constant for EI or enzyme inhibitor complex formation. Alpha prime is equal to 1 plus concentration of inhibitor divided by Ki prime, another rate constant, which actually vary in case of competitive, non-competitive and uncompetitive inhibitor when the inhibitor binds with the enzyme substrate complex, not with the free enzyme. Biological significance of enzyme inhibition. As we know that the inhibitor can regulate sometimes the enzyme activity, fine. So for agriculture, for therapeutic clinical purposes, the inhibitor can be used, Relenza. So it actually inhibits the neuraminidase activity of influenza virus. So they can be used. Cyanide is a metabolic inhibitor of respiratory enzymes in aerobic respiration enzymes. As well as aspirin, it inhibits the first enzyme in case of prostaglandin synthesis, which is actually responsible to cause pain. Okay. So for agriculture as well as for other medical therapeutic purposes, inhibitors can be used. Ribozyme. So always enzymes are not protein in nature. There are some of the enzymes which are RNA in nature, right? So they are called ribozyme. They are catalytic RNA. The example is RNase P. RNase P is needed for trimming of pre-tRNA to form proper mature tRNA. Ribosome itself, it's a ribonucleoprotein. The peptidyl transferase action of ribosome is nothing but ribozyme activity. Abzyme, monoclonal antibody, right, which is acting as enzyme. So sometimes it is called as catmab also. It binds in some cases DNA and it is 100 times faster to hydrolyze them, which is needed for cancer therapy as well as HIV therapy as well. It lowers down the activation energy. So antigen antibody reaction once again is showing the enzymatic activity. Isozymes, okay. So isozymes are the enzymes which is driving the same reaction but maybe have the different amino acid composition and kinetic parameters as well as different subcellular and tissue localization. The major example of this isozyme is lactate dehydrogenase. So it's a tetrameric enzyme or protein. It may have H4 where all 4 chains are H, which is abundant in heart muscle. In skeletal muscle, the isozyme is M4 where all 4 chains are M. In between them in RBC, in kidney, liver, we can find H3M isozyme, H2M2, HM3, etc. So where is the variation? The variation is there with respect to the Km value, right? So lactate dehydrogenase means it is governing a particular specific reaction needed for the respiration. In case of skeletal muscle, the lowest Km for pyruvate is there where the anaerobic respiration is needed. So from pyruvate easily lactate is produced. But in case of H4, in case of heart muscle, abundant of oxygen is there. So we don't need such respiration over there. So the Km become higher for the pyruvate for that particular isozyme. So in this way, by the presence or absence of isozyme, they regulate the metabolic activity in different tissues. Allozymes, the enzymes which are synthesized from different allelic variations. Okay, they are actually found in case of some plant enzyme. So student, I have discussed about the enzyme general kinetics as well as when it is related to the inhibition kinetics. So enzyme acts via lowering of free energy or activation energy. The velocity of the substrate, there is a particular relation with the rate of reaction as well as substrate concentration. The velocity versus substrate concentration curve is rectangular hyperbolic. Michaelis-Menten equation shows a relationship among the initial velocity of the reaction, maximum velocity, substrate concentration and Michaelis constant. It is valid for single substrate. Now, linear form of Michaelis-Menten equation provide interesting insights into enzyme kinetic data and can be expressed either by Lineweaver-Bach plot, Eadie-Hofstee plot or Hens-Wolff plot. Enzyme inhibition is loss of enzymatic activity. There may be either irreversible action, that means permanent loss by making covalent interaction, or maybe the reversible, which is somehow some other respect. So, with respect to time, with respect to the removal of the inhibitor, we can once again regain back all those inhibition, or the enzyme can regain its own structure as well as function. The reversible enzyme inhibition may be competitive, non-competitive or uncompetitive, and inhibitors can be used for therapeutic purposes as well as agricultural purposes. Thank you.